Today we're going to do for bending what we did for torsion and axial loading. That is, do things formally and introduce all the differential relationships and deal with the little more complexity that we dealt with when we did the first introduction to bending. And just to get us started, let me remind you where we are at this point. What did we do last time? So we started bending, as always, simply by thinking of just a beam of homogeneous cross-section with some modulus E. And this was a beam that had a height h. And in 201, we deal only with slender beams. Slender beams means that the height of the beam is much less than the length of the beam. And this assumption here is the one that allows us to say that the deformation and the stresses that come from bending from the moment is much higher than the stresses and deformation that come from the shear. So that the fact that the beam is long and slender is what allows us to kind of leave the shear story a little bit to the side for now. So our beams are slender, and we started with a homogeneous beam, and we just loaded it with a moment at the end, m0. And under the effect of this end moment, the beam curved up, and it curved up with a certain radius of curvatures rho. So we defined the deformation of the beam in terms of the inverse of the radius of curvature. We call this the curvature. And we take the curvature as the measure of deformation. So things that have large curvature means they're very curled up, have a lot of deformation. Things that have low curvature or zero curvature is this configuration here. The radius goes to infinity, the curvature is 0. And then as the beam curls up, the curvature increases. So we defined both the internal resultant of this kind of loading, which is an internal bending moment. So it's a moment with an axis along z, and we defined the sign convention for our measure of deformation. That's 1 over rho, positive when the beam curls up. And for our measure of internal resultant, which is m, and both of them are defined positive when the beam kind of smiles up. OK, so we did this thing, and then we obtained a relationship between the resultant inside the beam and the deformation of the beam. So that's the relationship we ended up with last time, right? And the relationship connects the resultant to the deformation through something that depends on the geometry of the cross-section and the material properties of the cross-section. So this quantity here, last time we were able to simplify because the beam was homogeneous. So we took the modulus, which is the same over the cross-section, out of the integral. And we ended up with a relationship that tells us that the moment is equal to the curvature times a section stiffness EI, where E is the modulus of the material, and I is what is left inside the integral, which is y squared dA, which is the moment of inertia of the cross-section with respect to the y direction. So let's go back a little bit to remember the story of y and the neutral axis. So remember that the curvature is defined at the neutral axis of the beam. The neutral axis of the beam is a line along the beam where there is no strain. Is the line along the beam which has the same length when the beam curled up that it had before it was deformed. So at the neutral axis, the strain is 0. And for convenience, we define the y coordinate as starting at the neutral axis. So our axis y is defined, y equals 0 is defined at the neutral axis of the beam. The other simplification that we do in 201 is that we choose beams which have double symmetric cross section. So the beams are symmetric top and bottom as well as left and right. So because the beams have all these symmetries, and because there is no axial resultant force that is carried, it means that as much of the beam must be in compression as it must be in tension, so that together they give me 0 resultant, which means that the middle territory, the place where there is no strain, is right at the midplane of the beam. So because we are dealing with symmetric cross-section, our neutral axis is going to be right in the middle of the cross-section, and that is where y equals 0 is defined. So y equals 0 is defined on the midplane so that the y-axis starts at the midplane. The radius of curvature of the beam, rho, is defined at the midplane. On that midplane, there is no strain. And then, because the beam curls up, you see that the top of the beam gets shorter and the bottom of the beam gets longer. There is going to be a compressive strain at the top. There is going to be tensile strain at the bottom. And we obtain, if this is the cross-section of the beam, if I go to a distance x, and I cut the beam, so this is my beam. This is my beam here. So if I go here and cut the beam and look at what happened in section x, this is my section x. At section x, I have y coming out right from the middle of the beam. The radius of curvature is rho of x. And we obtain the fact that on this cross-section, the bottom of the section is in tension, and the strain at the bottom of the section, therefore, is positive. It's elongating at the bottom. The top of the beam is in compression. It shortens at the top. And the strain distribution, if I plot the strain distribution along the y-axis on this cross-section, this strain distribution is linear in y. Is minus y over rho. So the strain that I have on section x depends on the curvature of section x, and it changes depending on where I am on the cross-section linearly with y. And then we said, guess what? If I know the strain, I know the stress. It's just our good old relationship through the Young's modulus. And so through this, I can find the stress. And actually, this relationship plus this relationship is the one that allowed us to derive this relationship here from equilibrium. OK? So that's where we were last time. So what we want, is that OK?
And then EA wasn't it H over 2 rho?
Oh, this thing, yeah. So the strain here, exactly right. If I substitute, if the height of the beam here is h, then if I substitute minus y over rho here, the strain here that I get is the y is h over 2, and I get h over 2 rho over there as the maximum strain on that cross-section. Exactly right. OK? All right, so what we're going to do today is we're going to take away all these simplifications that we introduced on Thursday. On Thursday, we said the beam is homogeneous. No, forget about that. I can do composite beams as long as they are symmetric. So I can do composite beams like this, in which even if it's made of two materials, this is one material, this is another material, this is the same material as the top, I can have composite beams as long as they still have the double symmetry. I cannot have any which-way distribution of material on the cross-section. It must be symmetric, OK? So I'm going to totally forget about the fact that the beam needs to be homogeneous. I don't think so. And I'm going to consider not just a constant moment in the beam, but a variational moment. So the curvature changes as well. And we're going to derive all the relationship. It's not going to be much different from what we have here, but we're going to do it a little more formally. OK, so we're going to do that. Let's start from the deformation of the beam. And remember, the beam is slender, and it has double symmetry. So we're going to do the deformation of this kind of beams. So the first thing that we need when we describe the deformation, remember how we got to the end, both in axial loading and in torsion. What is the thing that allowed us to kind of derive all those relationships about strain and deformation and so on? What is the first step that we need to do when we do these paths through deformation?
The bending, that's curly out.
That's the bending, yes. But the thing is, the question that I have is, I need somehow to connect curvature and strain. And remember, when we started in axial loading and we said, the first thing that we said in axial loading, we said all the section moved together has the same U deformation. And when we did torsion, and we had a long shaft, the thing that allows us to derive the relationship is that on section at x, the whole section rotated by phi x at x. It all rotated together. In axial loading, the whole section moved in ux together. The fact that it moved together, it allows us to say the strain is the same at every point in the cross-section, remember? And in torsion, the fact that the whole section rotated together allowed us to say the strain varies linearly with the radius, right? That's what allowed us to connect the sectional deformation, which remember was du dx and d phi dx, to the strain. So we do the same thing in bending. So in bending, we do the same kind of trick. We say, here is the beam. And what I do is I draw on the beam vertical lines orthogonal to the axis of the beam, like that, just with a pen. I go there and I draw these lines. And then the beam deforms, like that. And the assumption that I make, so the first step always in this treatment is to say that there is a kinematic assumption. Kinematic assumption. Assumption about the movement of the beam. The kinematic assumption is that if I drew with the pen this vertical line orthogonal to the axis of the beam, when I then see the beam and I look at the same line, those lines remain straight, like that. And what that means is that each section rotates rigidly around now the z-axis, because now everything happens around the z-axis. In torsion, everything was rotating around x. Now in bending, everything rotates around the axis coming at you. You see? So this section, each of these sections here, if I drew this section and if I drew this section and this section and this section and this section and so on, each of these sections still remains flat. So the kinematic assumption is that the sections stay flat and rotate. Now they rotate around z. So now the rotation is around the z-axis. You see? Now remember that the rotation around x was called phi x.
What's this flat?
What's that? The sections. So if I go and if I imagine that this is my original beam, and I go and I paint a whole section there, like I color a flat surface here in the middle of the beam, then I deform the beam and I look at the color section. If I look at it, say I painted it red, and then it deformed, I look at all those colored points on the section, it still is flat. It's still a flat plane. You see? So it all kind of deforms together, and each section remains flat. You see? So each of these flat planes remains a flat plane when the beam deforms. It just rotates around the z-axis. And this rotation around the z-axis, if I wanted to be consistent with the phi x that I use for torsion, I would call it phi z. But normally this is called theta, theta of x. So theta of x, if I go to section, if I go here to section x, and I look at what the section x is doing, section x is rotating by theta of x. You see? It rotates around z by theta of x. Okay? And so theta of x changes from the beginning of the beam to the end of the beam. So here, for instance, at the wall, theta at the wall is 0, because the beam is stuck into the wall, and the wall does not let the beam rotate. The same way as the rotation in torsion was 0 at the wall, this rotation here, at the wall, I prevent the beam from rotating. At the wall, the rotation is 0. But then the rotation changes with x, and is defined by this function theta of x. Now, an interesting thing is that if I look at this angle, now what if I draw here the line that is tangent to the midsection of the beam at x, and I look at the angle that this line makes with the horizontal? This line is orthogonal to this, and this line is orthogonal to the line of the midsection. So this angle here is also theta of x.
What line is it?
This one here is a horizontal line, and this line is the line that orthogonal to this line, is the line tangent to the neutral axis, tangent to the beam. Is the line tangent to the beam at that point, right? If the beam is like a line, is like a curve, if I take the line tangent to the beam at this point, it's going to have a slope, okay? So from geometry, we see that theta of x, which is the rotation of the section, this is the rotation in z of the section, is also equal to the slope of the beam. Okay, just from geometry. So the section rotate that theta of x, and that rotation is equal to the slope that the beam makes with the horizontal at that point. Just geometry. You see? We good? Okay. So in a way, the slope that the beam makes is some measure of the deformation of the beam, right? When we were doing torsion, when we were describing the deformation of the shaft, how much a shaft changes from when it's loaded, from when it's not loaded to when it's loaded, our phi of x was our measure of how things change along the beam. When we were doing axial loading, our ux, how much each section moves, was our measure of what happened to the beam, right? So theta of x, the slope of the beam at every point, is a measure of the deformation of the beam. But you can imagine that that's not necessarily the measure that we are more interested in, because the other thing that the beam does as it deforms is it moves up from the original shape, right? So you see, we need something else to tell us things that we are more interested in. If I tell you, is this beam behaving like if I design the beam in the floor of my house, and I want to make sure that the beams behave the way I want it, I'm not going to ask you what is the slope at every spot on the floor. I'm worried if it deflects too much, if it moves vertically too much. So for beams, beam deformation, we cannot just stop at the angle. We need to go one step further.